number 5 in the observation reports right after Taras.
Great, thank you.
Okay.
Let's pull up a picture here.
So we got it 3 minutes before we go live, although people can already see us on YouTube. Not a problem.
So I have a question because there is a video embedded in my presentation, but it's also a YouTube video. Is it better to provide a link and then we go and watch it from there, or?
Well, if you can play it from your presentation, it'll work fine. Just make sure you click on share computer audio.
Sure.
I know
Yeah.
you worked with Zoom before.
Oh yeah.
Yeah. So when you go to share your screen, there's a little checkbox, share computer audio.
Okay.
If there's audio in the video, yeah.
Okay. Yeah. And we can also put the I can copy paste the link into the chat for you to share if you like.
Sure.
In case
Sounds
people
good.
want to watch it later.
Okay.
Okay.
Sounds good.
In the meantime, Dave, I'm now recording. We are live on YouTube and Facebook.
Okay.
You should be seeing us in presentation mode. All we have to do is get out of practice mode in any moment.
Yeah, I think we are. We may as well start up then. And I'm just looking here. Yeah, I can see everything properly. So I'll start the webinar and let people start jumping in. There we go. Yeah, they're starting to come in now.
Numbers are climbing, so we are live.
We are live, yeah. So folks, we're just waiting for everybody to continue logging in here. We'll just give it a couple more minutes and we'll get things underway.
Dave, I forgot to ask you, how long do you, how long have you reserved for my slot?
35,
Okay.
40, 35,
No,
40. Yeah.
No, I just need to know how fast I need to go. I can go slow. It's good.
Yep.
I probably won't need to take all of that time, but it'll allow options for questions.
Not a problem. And we have some more announcements and stuff as well.
That's what I figured.
Yeah. So not a problem. Okay, I think the numbers have more or less stabilized here, so I think we will get things underway. And Jim, do you want to do a quick audio test just before we get going here? Just make sure you're working.
Sure, check.
Oh, yep, you're good.
Check one. Sibilance.
Yep, sounds good. Okay, folks, welcome to our May meeting of the Ottawa Centre, RASC. Special welcome to other RASC centres. And a special welcome to our guest speaker this evening, Dr. Chris Hurd, who will be joining us or be presenting in the second half of the meeting here this evening. Next screen, please, Chris. So as we are on Zoom, a couple of security things here. First of all, if you have any questions for our speakers or for myself, please put them in the Q&A box. We do not monitor the chat box during the meeting. And do not raise your hand. We're not monitoring that as well. If you have a question, just Q&A, very simple. For your security, do not click on any web links that might appear in the chat or the Q&A windows. I do know that Dr. Chris Hurd will be sending one link out, and that is a safe link to a video. But sometimes hackers get into these things and they send us nefarious URLs. But if it comes from Chris Hurd, you are safe. Okay. So here is tonight's program. We're in the middle of the introduction. We got the Ottawa skies for May. We have Simon Hanmer, who's going to be talking about Mars, a new atlas for the 2020s. And we have very much a Mars focus tonight. Sharon Odell is going to give us a brief update on the Dominion Observatory and the challenges with the big hospital being built next door. 5-minute break, and then Dr. Chris Hurd will be speaking to us about the Mars Perseverance and the rock collecting and how he's involved with that. Observations and announcements. I'm hoping that tonight we will wrap up the meeting by 9:30, 9:45 at the very latest. We've been trying to manage our number of observations a little bit better tonight. Welcome to the new members, Bernie, Carly, Emily, James, and Brendan. And we have 23 new members in 2021. Members in the news. We just actually found out that Thomas Ray actually passed away last fall. He's a life member associated with our center. And we just found out recently that he had passed away. So we remember Thomas Ray this evening. Okay, turning to the Ottawa skies for May. Let's see what's happening up there. Okay, first of all, in terms of the moon phases, full moon is on May the 26th, and it is the second of 3 super moons that we're going to be having this year. The full moon, traditional name for that is the flower moon, because it's a time when the spring flowers are in abundance. It's also been known as the corn planting moon and the milk moon. Okay, so those are the moon phases for the month. This peaked last night, but it's still there. We had the Acrids meteor shower, and maybe if we have an evening without cloud, we might be able to see it. Comet 15P Finley. I realized that I've given you the positions for June through August, but it is up in the sky. I got the wrong slide in here. I apologize for that, but you're well prepared for June. It's coming up soon anyways, so that'll be up in the sky as of June 1st in these positions. Obviously, our days are getting longer, so 10 to 6 at the start of the month, and by the end of the month, the sunrise is at 20 after 5, so days are getting longer until June the 21st. Mercury, we do have the greatest eastern elongation, so look for the planet low in the western sky just after sunset on May the 17th, and actually a number of days either side of that, you should be able to see it just after sunset. Venus is visible after sunset, starting this month. Mars is visible in the evening, all evening. Jupiter is now visible before sunrise, as is Saturn. They're sort of tracking each other right now. They're fairly close together. Uranus is visible before sunrise the second half of the month. Right now it's sort of rising and setting with the sun, and Neptune is visible before sunrise. And coming up, there is our cartoon of the month. Sorry, it's a little bit fuzzy. It says, nope, moon still looks the same. You say this is the most powerful one you have? Anyways, there's our cartoon for the month. I'm still offering a virtual interactive introduction to astronomy. It's a 45-minute program for Beavers and Sparks and a 1-hour program for all other groups. I do a lot of outreach to Cubs and Scouts, but I also do adults as well with the 1-hour program. You'll get a sampling of both of these on our International Astronomy Day. I'll be presenting both of these. But if you have a group that you think might be interested in receiving this, send me an email, meetingchair@ottawa.rasc.ca. I've got a fair amount of space right now, so give me a shout. And then I have a follow-up to the adult and the older kids one called Astronomy. The next presentation goes into a little bit more depth, still an introduction to astronomy. Okay, I'm going to turn it over to Simon, who's going to be talking about the Mars Atlas.
It's Chris with a question
There
for
we
Simon.
go.
Are you going to run your own slides, or are you going to have me do it?
No, I'm going to run them, Chris, and we'll hope that everything works perfectly well.
Here you go.
There we go. If I can, there, and just move you folks over out of the way, and turn this on. That looks good. Okay, there we are.
Well, Chris, or Simon, we're seeing your, we're not seeing the full presentation on the screen.
Okay, let's see why not. Try this.
You need to start the slideshow.
Is that still not?
No, that's good. That's good.
Okay,
Yeah.
good.
Yeah.
All righty. I just need to get this out of the way so that I can see everything. There we go. Okay. But let me go. There we go. That's the beginning. That's where I want to be. So there is a new Mars Atlas. Some of you will be very familiar with the Atlas of the Moon by Ruckel. Many of you actually use it as a part of your observing programs. And the new Mars Atlas is by a group called Red Mapper, and it came out last year, 2020. Before I forget, it costs, I went to the website just today just to check, it costs something just under $40 US. As I say, it compares, if you're familiar with the Moon Atlas, then you'll be aware of the kind of thing that this Mars Atlas represents. Although, as you'll see, because I'm going to show you some images, this is a color version. And I think it's certainly an upgrade on the quality of the Moon Atlas. It comes in two parts. It's actually a book and what they call a web portal. And what I'm going to be showing you are images that I've managed to grab from the web portal. I'm not going to take you obviously through the entire atlas. I've selected a number of images of either things that you will be familiar with or things that I think can actually illustrate to you the kind of thing that you can actually see for yourself in the atlas and maybe even start to interpret. Now, with respect to Ruckel's atlas, it's very obvious why amateur astronomers might want one. There you are looking at the moon and you're thinking, well, what is that crater over on the left-hand side? Let me look it up in Ruckel. You're not likely to do the same thing with the Mars Atlas, but more and more we're seeing detailed images presented to us on the internet by the international and national space agencies, NASA, European Space Agency, etc. And you might well want to know, well, where exactly is this on Mars? And this is exactly where this atlas would kick in. Now, what I'm going to do here, let's move to the first slide. This is what a screenshot looks like from the web portal. And you'll see that there are lines of latitude here in pale white, and there are lines of longitude. And a page of the book corresponds to one of these rectangles. So this would be a page, this would be a page. So the images that I'm going to be showing you tonight will actually represent multiple pages. And then from time to time, I'll zoom in so that you get an idea of what you can really see in high resolution on the book pages themselves. By the way, as we're going along, just so that you know where you are, there will always be this inset of the digital elevation model of Mars. So just to place you, there's the Tharsis Plateau with the famous 3 volcanoes. There is Olympus, there is the Marineris Valley, and then the large Argyre and Hellas basins. These are the northern plains in blue, and in the various yellows and reds, those are the highlands. And this white disk tells you where you are. So this particular image here is roughly here. Now, zoomed out like this, you look at this and think, well, okay, what can I see? Yeah, I can see big craters. There are undoubtedly smaller craters in there. There's words that I can't possibly read. And then there's what looks here like it might be a volcano over there. Well, obviously one can zoom in, and as you zoom in, there's the crater we were just looking at, and you can now start to see intricate detail. And here, just to the south of the crater, you can really see in grand detail, in pretty good resolution here. You can see these mesas. If you're a fan of Western movies, you'll know that the cowboys ride from down the canyons between mesas. Well, that's what these are. Flat-topped hills. I won't call them mountains. They're flat-topped hills. They're the remnants of erosion. And as I say, here are the lines of longitude, which mean that, let me go back, I've clicked. This is really more or less a page. So this gives you an idea of the kind of resolution you'll see in the book itself. This is an interesting one. This is a crater that you will actually know by name. This is Gale crater. And of course, Gale crater is where Curiosity, the Curiosity rover, is, as I believe, is still roaming around. This is Mount Sharp, as you'll have been following. And you can also see that on the image here, there's a little red marker. There are actually markers all throughout the book telling us where the various rovers and landers have actually touched down. Again, you can see the excellent resolution. The craters here are very visible. You can see a lot of very, very good topography, channels, and again, these mesas. This one you'll recognize. This is the northern margin of Olympus, of course, the largest volcano, or if you prefer, the largest mountain in the entire solar system. And off the northern end here, this happened. This huge mess is the largest landslide, if I can call it that, the largest landslide in the solar system. And you can see that there's a lot of detail in here. Well, remember, this is at least 3 pages worth. If you actually zoom in, you can see far more detail. Now you can actually see not only the details of the wrinkles and rumples as the material flowed away from the edge of the volcano, but you can also see channels which have been cut through all of this in incredible detail. And again, this is 1 page's worth. This is the next page over. So you certainly won't be short on detail with this. Now, as you move along, you get pages or scenes like this. This is Tractus Catena. And you can see where we are here. We were just looking at Olympus over there. We're on the northern edge here of the Tharsis rise. And you can clearly see these scratches. We call them scratches, if you like, in lay terms, but of course they're actually fractures and fissures. Some of them are in a massive group. There's a whole load of these. They're almost penetratively developed, and others are very distinct and clear. This, I won't get into any of the geological details, by the way, but what I will point out is that this is the kind of thing that geologists would be looking at this atlas and saying, I wonder if that's a major fault. Over here, of course, is a channel, and they'll be wondering, of course, what flowed down that channel, what actually made that channel, which way was it going, and what actually filled it. These things here are most intriguing. They might be wondering if perhaps these things represent the surface expression of major dike swarms, perhaps associated with major volcanic centers, talking of which, there's a major volcano over here, which I think is very, very clear. Yes, you can still see craters, impact craters, and then you see these little dots. These little dots here, they're actually less obvious in the book. They're there, but they're less obtrusive, I find. And what they are actually small named impact craters, which is very useful. The next image here is something completely different. This is Kasei Vallis. I've talked to you about this before. Some of you may remember that in 2014, I got into my car and drove 14,000 kilometers there and back to Washington State, where I went to see the supposed terrestrial equivalent of these outflow channels, which are supposed to represent catastrophic floods, which would have carved these valleys almost in an instant. There probably would have been 1,000 instants in order to do this, not just one. But this is what they look like in the atlas. And remember, this would be a page, and this would be another page. So let's zoom in a little closer so we can actually see what we can see. And sure enough, here is the outwash valley, and you can see these islands within the valley, which are supposedly the remnants, eroded remnants from the flood waters. So they're very clearly illustrated. And again, this is just one page. Let me just think of where I went with that. Okay, very good. Yes, what we're looking at here, we're actually in a corner of one of the few places on Mars that you can see through amateur telescopes from your backyard, Syrtis Major, which is the black or the dark thumb sticking up here when Mars is at its most proximal to the Earth. This is one of the few features we can actually clearly see. And again, what you're seeing here are channels, fractures, and these erosional remnants, these flat-topped hills called mesas. One of the major volcanic centers on Mars, of course, is Elysium Mons. This, of course, is the volcanic center over with on Tharsis Rise. Elysium Mons is sitting over here out in the lowlands. And the feature I wanted you to see here are these channels here, broad, rather irregular looking channels on both sides or both flanks, if you will, of Elysium Mons. Elysium Mons, of course, extends right out to here. So these channels really are sitting on Elysium Mons itself. They're undoubtedly magmatic. They're undoubtedly related to the volcano. Are they perhaps the expressions of dikes which were actually feeding magma into the volcano? I don't know, but that's the kind of question that geologists working on this would be asking themselves. If we get it off of channels and flows into, or rather off of magmatic channels and flows, and into perhaps more catastrophic flows here. These are outflow channels here, which you can see here. They're in the Planitia area at the eastern end of the Mariner Valley. The idea being that waters flowing catastrophically down the Mariner Valley would have then turned up into the plains of Planitia, and these would be the channels up which they went. And this is a particularly interesting area here. It's actually an area of surface collapse forming a chaos. Well, it's a little difficult to see here, but if we zoom in, there you can really appreciate the level of resolution and detail that we can see. Here's a major meandering channel. These would be the large outflow channels, another major channel over here. And then this here would be the collapsed terrain, perhaps collapsing because permafrost or ground ice was being melted for whatever reason catastrophically, and then contributing to this flooding here. We've moved over here now to an area called Amenthes Fossae. Fossae means ditches. And the point here is you can see this series of, they're well spaced, but they're very straight channels. They start and they stop. They're not continuous. Some of them are quite short. They even step over. Look at this one here. This one comes along and then it's relayed, if you will, by this other one, which is slightly over to one side. And geologists would look at this and say, this looks like faulting to me. Looks like fractures with movement on them. This is the kind of thing they'd be looking at. Now, something that really needs no introduction to any of you, I'm sure, this, of course, is the Mariner Valley. And the entire Mariner Valley, of course, is captured within the atlas, but it's so big that it has to be captured page by page by page. But you can see all of the various components in here. The cliffs stand out beautifully. and the details inside are very, very well resolved. If we zoom in at the western end, then what we see here is what's known as Noctis Labyrinthus, which means the nighttime labyrinth. And you can well understand why. I meant to look up what these little red dots are. I must admit I forget, but these things on the portal, you can turn these things on and off. So you can get as much detail as you want. And of course, on the portal, you can zoom in, which is exactly what we're going to do here. But before we do, let's just remind ourselves that this labyrinth here is made of these rectangularly disposed channels, valleys. They're undoubtedly related to faulting and fracturing. Actually, it looks rather like the crust of a loaf of bread as it rises in the oven. And that's possibly what this actually represents. And this is the kind of thing, again, that geologists would be looking to interpret. But look at the details you can actually see in the main Mariner Valley, these feeder valleys coming in with all these little tributaries coming off. The detail here is extremely well captured. This is moving on to a different theme here. This is Daedalia Planum, which is basically in the southern part or just south of the Tharsis Plateau. And the main theme image here is this rather large channel, which is heading north. And it's obviously heading somewhere. We'll look at where it might be heading in just a moment. But there are also, again, these fine scratches, which are in fact finely, closely spaced fractures. They may be faults, but they're very possibly actually fractures filled with magma, which geologists would call dikes. That's the kind of question that geologists would be asking themselves. And then, of course, they've been hit with these impacts. And by looking at the impacts and which impacts actually cut these fine structures, or which of these fine structures cut which impacts. There's an impact there which is cut by these structures. This one here cuts across these structures. You can now work out a time sequence. And if you can work out, as geologists can, or planetary scientists, I should say, they can actually work out the relative timing here of these impact craters, and that then helps them work out the history, the geological history, the stratigraphy, if you will, of the planet and the planet's surface development. Now, I was talking about channels heading north. Well, here's a channel, which again, it's famous. You may actually know what one this one is. It's called Nirgal Vallis. And the important thing here is that this one here actually feeds into another channel, and this channel feeds into this crater. And let's just have a look at this a little bit better, because this crater, nothing's coming out the other end. So this crater must have formed a lake. If Nirgal Vallis water was flowing down it this way, and therefore flowing perhaps this way up this channel, then you're looking at lakes here. So again, on this atlas, you can see sufficiently good detail and resolution that you can see rivers and lakes, and which rivers would be filling which lakes. And on that particular subject is this. We're looking here at, let me just go one ahead just to see, no, we're doing well. We're looking here, this crater here, this is Gusev crater. You may remember that name. You remember Spirit rover that landed? And you may remember that the day it landed, immediately the NASA scientists said, oh, look, we've landed in a lake. Then they had a good look at the pictures coming from the Spirit rover and began to realize that actually that didn't look anything like a lake bottom. That was actually a rock desert. And then they had to sort of backtrack very quickly and realize that, well, it might have been a lake, but what they were looking at now was all kind of desert sand, which probably got blown in from elsewhere. Why was it a lake? Because you've got this major channel here. This, I believe, is Mardim Vallis. Water would have flowed along this meandering channel and filled this lake here, which has no other outlet. So again, you've got all of these craters, you've got other channels here, and as the craters either hit the channel or are cut by the channel, it helps you determine what the age of the channel might be. Here we're moving to something much bigger. This is the Argyre impact basin. This is probably of the order of hundreds to probably about just under 1,000 kilometers across. The reason for showing this is because as you look around the edges, everybody focuses on the basin. And with good justification. Here it is, it's right there. That's not, this one over here is Hellas. This is Argyre right here. It is indeed fascinating in its own right, but one of the things that's really fascinating is that around its edge here, you actually have a series of cliffs. You can just about make it out here on the image that I've given you here, but if we were to focus in, oh, we can, hang on a second. We'll do that in a moment. We'll be able to focus in on this cliff here, and then there are all kinds of flat-topped hills, these mesas. So let's focus in on this part right here, zoom in, and there we go. So we can actually see a cliff here, just like a seaside cliff, except this has got nothing to do with the sea at all. These, of course, are fractures related to the impact, with the block on this side dropping down in relation to the block on that side. So the cliff, let me go back to where I should be, the cliff faces in towards the impact basin. But you can see the details of the erosional relic hilltops, flat-topped hills here. And again, look at the impacts. This impact here seems to actually cut into these eroded mesas. So this would be younger, and the mesas would be older. In other cases, one might actually be able to see there a fragment of impact basin, or rather a crater there, sitting on top of the flat top mesa. So that would therefore have been older. And this brings me to my last slide. It's a very appropriate slide. Again, this is the area of Syrtis Major. Again, something which I'm sure many of you have looked at through your telescopes, that dark thumb sticking up. Sometimes it's the only thing you can distinguish. And yes, you can clearly see these channels here. They're quite widely spaced. So there could be all kinds of debates about how they formed. They're not meandering, they're quite straight. So are they tectonic? Are they erosional? All kinds of issues, all kinds of questions. And again, around the top end here, these erosional remnants, these mesas, and these various channels. This is the kind of thing which geologists and planetary scientists would spend forever on. But in fact, what they're going to be doing is they're going to be spending forever on this area down here. Because this down here, that word there is Jezero. And Chris will pick up on this immediately, since he'll be talking to us about this. This, of course, is the crater where the Perseverance rover is currently sitting. And in the atlas, they're well ahead of the game. They've got it marked and they've got it named. So this is a good place for me to stop. It also is a very good segue for Chris's talk after the break. I'll leave it there with one further point. This atlas is extremely good quality. I've quality checked it in detail. There are 1 or 2 spelling errors. Really nothing to write home about. At $40 US, I think it's $38.50, something like that. It's something that I am really so glad that I have on my bookshelf. Any of you that follow what's actually going on Mars through the internet, through the various rovers, the various orbiters, there will be more orbiters. We know that various other countries are sending their orbiters. China, India. I'm not quite sure where some of the other orbiters are coming from and going to, but we're going to be seeing over the next few years a lot of information coming from Mars, and you're going to want to know, what am I looking at? Where is it? And how does it relate to the other things that I've just been looking at? This atlas, I think, is a very, very worthwhile purchase, and I'll leave it at that. No, I'm not getting paid to actually advertise this. I'll stop my sharing. There we go.
Okay, Simon, so we've got some questions for you.
Okay.
First one is, are the colors an accurate representation of the Martian surface?
They're actually very good. They're in shades of red and tan. They've had to play around with the colors a little bit, because not only do they want to show you what the surface might actually look like, but the thing is, they also want a little bit of color to highlight topography. So as you go up, in topography, they want you to be able to see this without having to stare at every one of the contours, because you can see the contours, and the contours, they do tell you what the heights of the contours are. But in order for you to be able to just at a glance say, oh, that's a mountain and that's an impact basin, they're using gray, bluish gray for low areas. They're using, which of course is not the color of the surface. They're using more reds and yellows for the high areas. That's just standard practice. And then everything that's more or less on the average topography is in natural color, which is very, very agreeable to see.
Okay. With respect to the Olympus collapse, do we think that it was a short catastrophic event or a longer event, like a rock glacier?
No, it probably was not a rock glacier at all. Was it one single event? Let's put it this way. Given how big Olympus is, and you can see that landslide goes at least the equivalent distance of the entire diameter of Olympus. It's gone hundreds of kilometers. The far end would have had to have ridden over the top of what was close by, or the back end would have had to have built up on what went before. It probably was one major event with then subsequent, what's the word I'm looking for, aftershocks, if you will. But it must have been one hell of an event to see, if you could, with all the dust.
Absolutely. And a final question here, are these actual satellite images, photographs with map symbols superimposed?
No, this is an atlas. It's not a photo montage. Just like the Rukl Atlas, and that's why I started with the Rukl Atlas. The Rukl Atlas was hand-drawn. This is a step up. It's computer drawn. And they obviously have used the photo imagery to get the accurate topography. But it is a drawing. But it is an extremely well-rendered drawing, and a drawing at very high resolution. It is a map. And as a geologist, I very much appreciate that. If they were to have used photographic imagery, the variation within the image would have gotten in the way of the variation you want to see in terms of contours and what have you. Supposing you pick white as your contour color, and all of a sudden you've got white in the photograph, you're going to lose the contours. So they basically done this as a map. They've chosen their background colors and then said, fine, now we can choose one color for all the contours so it can be very clearly seen.
Yeah, some of the data came from the Mars Orbital Laser Altimeter as well.
Absolutely.
Yeah, so there's a variety of sources that they went to get the accuracy that they did have.
Which is one of the wonders of this atlas, is they've had access to this data and they've used it.
Okay, one more question's popped in here. What do the famous face and pyramids of Mars now look like from the atlas?
You can't even see them, because you can only see them if you can see certain configurations of shadow. And the whole point here is that this is an atlas, so therefore there are no shadows.
Okay.
So therefore they just disappear. This is the same thing as shadows disappearing at full moon. There are so many things you can no longer see at full moon because you don't have any shadows. Okay. That was done intentionally here so that you can see the detail they want to present to you.
And I think that you probably already answered this, but since some of the photos will be at an angle, should it be possible to construct something more 3D? This is not really photos, but
you could indeed, and the way to do that, of course, is exactly what the European Space Agency does. This is really their strength. They take these images and then they construct. It's not 3D, but they are perspective images, and you can spin them around. So the perspective will actually change as you rotate them. But to put that into a map of the entire planet would be, one, incredibly difficult, and B, I don't think many of us have computer power to actually manage to power that.
Okay, so that is it for the questions. So thank you very much, Simon. I really appreciate that. It's a good segue into our next presentation. We have a couple of administrative things prior to that, so I'm going to get Chris to bring up, and Jim Thompson, Let me just unspotlight you here. Remove spotlight. Okay, Jim.
Great, thanks, Dave. So good evening, everybody. For those of you who know about Astronomy Day, the event for 2021 is coming up next Saturday, May 15th. The RASC Ottawa Center and the Ottawa Valley Astronomy and Observers Group have worked together again this year to put a all-day program, online program together. This is sort of a snippet of the schedule for the first half of the day on the screen. We're going to start the morning with some demonstrations of various observing equipment like telescopes or observatories. We'll sprinkle in some live solar observing with that, as long as it's not cloudy, of course. And then through the afternoon, we'll have a series of very interesting presentations from local astronomers. Dave already mentioned that he's going to give his intro to astronomy presentation, but there will also be presentations on safe solar observing, presentations about what's new in the solar system by Simon, and we'll have a guest presenter from Science North giving a presentation on the upcoming manned or peopled lunar mission, the Artemis mission. Next slide, please, Chris. The second half of the day will include some more presentations talking about different aspects of observing. For example, Paul is going to talk about his portable observing getup that he uses when he's out on the road. Boyan's going to talk to us about night vision goggles and how it's basically changed observing for him. Andrea is going to talk about her beginning in astrophotography using a simple tracking setup, and then I'm going to talk about what it's like to be an urban astronomer. And that'll take us up until it gets dark, around 9 p.m., at which point we'll switch over to a live star party where people will be streaming live images of the sky from their home telescope setup over the Zoom interface for everybody to enjoy. So if you have not already pre-registered, you do need to pre-register for this event, just like the monthly RASC meetings. You can find out more information at the website noted on the bottom of the screen there, astrodayottawa.weebly.com. And if you have any other specific questions, feel free to send me an email. Thank you.
Thank you. And we're going to turn it over to Sharon Odell.
Hello, can you hear me?
Yep.
Great.
Good evening, everyone. I would like to note that the artwork on this slide that depicts the Dominion Observatory was created at the beginning of the pandemic in April 2020 by urban artist Michael Scroll. It shows that this building is still having presence for others even today. And following this, I would also like to give a brief update of the observatory site, the Dominion Observatory Preservation Committee, in order to give the new status of the observatory with reference to the anticipated Ottawa Hospital construction. Our team has been working hard on strengthening the National Heritage designation of the Dominion Observatory campus, which many of you know is located near Carling Avenue in Ottawa, situated at the Central Experimental Farm, which is also a National Heritage Site in its own right. Next slide, please. To give short context to this, during the 1970s, past Ottawa RASC member, Canadian physicist Arthur Edwin Covington was the first to fill out an application requesting that the observatory and its external buildings be designated as heritage. This was based on architectural and engineering merit. Although this application was acknowledged, and his idea of installing 2 brass plaques to commemorate the astronomer William Frederick King and Canadian engineer Sir Sanford Fleming was also applauded, based on contributions to Canada's astronomy program, train travel, and timekeeping. It wasn't until 1992 that Parks Canada completed an updated Statement of Significance report, also called an SOS, on the observatory and all buildings associated. This allowed the buildings on the campus to be individually registered as heritage, but only to the boundary of each of their footprints. Therefore, a subsequent SOS is about to be submitted on behalf of RASC to add stronger coverage of the heritage overlay for the observatory enclave of buildings. This is based on whether we can collaborate with the owners in order to place focus on how each campus building interrelates to each other as an integral part of understanding the historical value of them as an inseparable set. Otherwise, a wedge may be thrown between them if this value is not highlighted with expedience. Next slide. Within this momentum, there was an announcement on Tuesday, May 4th at the Ottawa City Councillors meeting for their Finance and Economic Development Committee, also called FEDCO, who reviewed the latest plans for developing the new Civic Ottawa Hospital. Some of these plans can be seen on this slide here. For more info on this, we urge you to visit the website noted above left, called the newcivicdevelopment.ca. Next slide, please. Looking closer at the slides that were in the FEDCO meeting presentation to Ottawa City Councillors, I have highlighted where the Dominion Observatory sits via red arrow and where the Dominion Observatory has an encircling mark on it. That is where the campus is situated near the newly proposed hospital, top left of the slide. To right of the slide, as per an image on Toronto Global News website, one can see how proposed emergency vehicle traffic will flow. This will go around the observatory campus and Central Experimental Farm site as well. Next slide, please. Of particular concern again are how close the observatory outer buildings will be affected by the new hospital site, and the light pollution, how it may be affected for future use of the site. We are looking into this as well. Here, as a quick summary, the following dates for the Civic Hospital development are 2021, this year, is the planning and for it to be finished. In 2022, a parking garage will be built next year. Not quite sure where it will be situated, but it will be one of the outlying buildings. 2023, the financial plan and purpose for it, that folder will close. In 2024, the construction will begin, and in 2028 will be the grand opening. Next slide. A copy of this information here, and anything else you would like to ask, please write to us at our new email address, dominionobservatorycommittee@gmail.com. And we would be happy to respond to any further questions. Thank you for your time on behalf of the Dominion Observatory Preservation Committee.
Okay, thank you very much, Sharon. And Chris, okay, I think you're going to talk to this one.
Thanks, Dave. Just an announcement for all the members in the group. Organization like RASC, whose foundation is all members, has a very critical back-end function of having a database of who we all are. And while most members don't interface directly with this database, those of us in the sort of administrative roles use it extensively. And the RASC just last week brought in a brand new database. This is a very significant change and upgrade and risk for the organization to implement. Where members will notice this is that if you go to the website, in the upper right where I have a big X, there was, in fact still is, a button for you to log in with a username and password. Most people wouldn't likely have reason to go in except to renew their membership. That function, even though it's still on the web page, is disabled and has been replaced by a new login that you see I've circled there in red called the Secure Site login. When you click on that, you now come to a whole new set of pages for the website under a different address called secure.rasc. And as you log into this, and why I'm really giving this announcement is your existing username and password will no longer function. As you log in for the first time, you'll have to give your email address, which must be the same address that you used to register as a member. And then it'll ask for your password and you don't have one. You'll have to say you forgot your password, register a new one, and you'll then once and for all be into the secure site and be able to get back into it. When you go to that secure site, there's a whole new range of functions. It allows you to go in and modify your account, your profile, your email address, renew your membership. But now it also gives access to several new features, including a list of all the forums. Some people may know these, particularly the best known one called the RASC's list, or any of these mail services that have the word listserv in their name. They're all accessed from here, and you can now go in here and see what they all are and subscribe to them. And there's new document libraries, and it may form also a new mailing list for within the members of our center. We haven't decided that yet. At least you should be aware that this is here, and that you will have to go through before you next renew, changing your username and password. Thanks, Dave.
Okay. Okay, folks, so just a second here. There we go. We do have a number of open positions on our council here. First of all, we are looking for a national representative. This is somebody who sits on the National Council, represents the Ottawa Centre. We have one person doing that right now, but we do need a second person. If you're interested in that, please email Chris. Would you be the best person to contact for this? Or you can contact me.
Either one.
Yeah, either myself, so chris@terran.ca, or meetingchair@rasc.ottawa.ca if you're interested in that. We're also looking for somebody to be our Public Star Party coordinator. We're not having any Public Star parties right now. There probably will not be any until possibly October timeframe. Depends on how the COVID stuff is going. But we'd love to get somebody in this position so that they can work with the previous Public Star Party coordinator and get up to speed on things. And basically, they're just responsible to ensure that there's somebody who is going to be, who's assigned as a warden at each of the different events, and ensuring that the lights are turned off and various other things. And also, they are responsible for picking the dates for the Public Star Party. And quite often, our Public Star Parties are out at the Diefenbunker, but we are looking at having them in some other locations around Ottawa as well. The last position is our light pollution person, and this is somebody who is speaking on behalf of the RASC to bring people's attention to the issue of light pollution. This could be somebody that might interface with the city of Ottawa, or they may interface with some developments where they see there's quite a problem with light pollution. And again, this position has been open for a while. If you see light pollution as a concern and would like to get active in this, this would be a good position to link into. Okay, so we are doing quite well time-wise here. We're almost right on schedule. So we're going to have a 5-minute break, and then we're going to put the challenges up. So maybe just flip to the next slide here, Chris. So we've got one Messier object, one moon object. See if you can figure out what these are. And after 5 minutes, we'll come back and see how well you did. You're quite welcome to put them in the chat window, or and put your guesses in there. We'll see you in 5. Okay, folks, we're about to get things back underway. Chris, if you could move on to the next slide, that would be great. Okay, so there's the answer to the Messier Moon Challenge. First one is M108, the barred spiral galaxy, and Gauss, the crater Gauss on the moon. So hopefully some of you got that. So I'm very pleased to welcome tonight Dr. Chris Hurd, and he's got his introduction right there on the screen. So I'm very pleased to have him with us. Chris worked with Simon many years ago as a graduate student, and so it's a bit of a reunion here tonight. So welcome aboard, Chris, and we're going to get you to share your slides and you tell us a little bit about the what you're doing on the Mars Perseverance mission.
Thanks very much. I'm just going to share my screen, make sure it's the correct one that I'm sharing.
And it's the other Chris reminding Chris Hurd, as you share, please make sure you turn on the computer audio for your video.
Yep, thanks, got that. Great. So thanks very much. It's really a pleasure to be here with you all this evening. Yeah, and to speak to the RASC Center for my hometown. Yeah, as Dave mentioned, I did work with Simon. I was an undergraduate field assistant actually while I was at Queen's for 2 summers on Southern Baffin Island, and that was really a phenomenal experience. I'm going to talk to you more about Mars today. I'm going to talk to you about the Perseverance rover mission. Towards the end, I'll talk about how I'm involved and the significance of that, but I am going to give you an overview. I'm going to tell you all about kind of why this particular mission, where, and the instruments that are included on it, its capabilities, and some of the first results. And then, of course, what we're looking forward to in the future. Of course, Mars has been explored by a number of spacecraft for a number of years. Here's a brief summary that goes back to the turn of the last century. You can see there's a number of orbiting spacecraft and landers. The Curiosity rover in Gale crater landed in 2011 and is still going. The Mars exploration rovers here lasted for several years. And Phoenix, there was a Canadian contribution to the Phoenix mission. The InSight lander is still going. And then the 2020 Mars rover is what I'm going to talk about today. The ExoMars rover here is a European Space Agency rover that has been postponed to 2022. But this is all just to sort of remind us of sort of the framework that we have. Not only have the results from the orbiting observations been put into really great products like the Atlas that Simon talked about, but we've also been able to piece together the history of Mars through the relative age relationships that we can see through basically remotely sensed mapping, and in some cases, of course, where the rovers and landers have set down something about that local geology. What we do know is that Mars must have had liquid water stable at the surface in ancient times, probably 3.5 to 4 billion years ago. It may or may not have had a northern ocean, those northern lowlands that were mentioned in the Atlas. May have been filled with water, possibly, but maybe not. But certainly there was liquid water at the surface, permeating the surface, we think, some 3.5 to 4 billion years ago, whereas, as you're probably aware today, liquid water is not stable. And really, one of the big questions is this big picture question is what the geologic evolution of Mars and why did it differ so much from the Earth. Now, this diagram is a little bit of an eye chart, I guess, but it's just really to give you, is to sort of show you that a couple things. One is that the Mars history or chronology of Mars, of what happened and when, is broken up into epochs known as the pre-Noachian, the Noachian, the Hesperian, and the Amazonian. And superimposed on this circular diagram is a number of events that have happened. You can see the Tharsis rise and volcanism, for example, the Vallis, Marineris, and Noctis, Labyrinthus rifting and timing, etc. Lots of things have happened in Mars history, but the main take home from this is that lots were happening, but most of it early on. And the liquid water at the surface was really in the Hesperian and Noachian epochs. And to go along with that, or sort of how we know this, but also to go along with that, here's a sort of summary of some of the major events in the Noachian, pre-Noachian, Hesperian, and Amazonian. And you can see that things like obviously impact cratering and what's called a late heavy bombardment happened within the first 500 million years of Mars history. Things like valley networks where liquid water was flowing have occurred mostly in this time frame, although perhaps sporadically more recently. But one of the things I really want to highlight with this, and this is probably the biggest paradigm, I would say, in the last 10 to 15 years that it has been deduced for Mars history, which is that based on the minerals that have been observed from orbit and the relative ages of the different rock units exposed on Mars, we now understand that the oldest rocks on Mars are characterized by lots and lots of clays. And those rocks that formed more in the Hesperian are characterized more by sulfates. And this is not just from orbit, actually. The Mars exploration rovers saw this as well, especially the Opportunity rover saw this as well. Sulfate minerals were dominant. And so the shift here can be explained by the pH, the acidity of the water that existed at the Martian surface prior to about 3.8 billion years ago being more neutral, such that the alteration would produce clays. And then something happened. We don't know exactly what happened, but it shifted. And the water became more acidic, and also the atmosphere thinned, the dynamo that produced a magnetic field died out all around this time. And then after that, into the Amazonian is really characterized by a complete drying out of the surface, such that the only thing that happens is rusting. Essentially, anhydrous, as it says there, that is without the action of water, ferric oxides basically rusting. And that's the whole reason why Mars looks like what it looks like today. And this is what one of you might see through your telescopes. This was actually taken by my friend Murray Paulson, who's an RASC Edmonton Center member, who provided this for me, and I looked it up because I figured that this crowd would want to know. But he took it over the evening of October 3rd of last year using a Muon 250 at f24. So one of the big questions then is, two big questions. One is, why did Mars go through this major global scale change to go from something that may have almost certainly had liquid water of neutral pH at the surface, obviously that means warmer, wetter, you might have heard that before, to completely drying out. And the second thing is, when it was warmer and wetter, did life exist? So that's really one of the driving things about this mission, Perseverance, is we want to answer the question, did Mars ever have life? Of course, the only place where we know there is life is the Earth. And this is a very brief, sweeping overview of life on the Earth over Earth's history. And of course, the major events are shown here, different types of organisms. The first sort of familiar fossils that we have is within about the last 500 to 600 million years, so-called body fossils. Prior to that, we're talking mostly single-celled organisms. And the first organisms that we have that are single-celled organisms that likely underwent photosynthesis are from about 3.5 billion years ago. And this timing that we're talking about for Mars is right around that time. So the thinking is, obviously, we're not going to look for the classic fossils. We're going to look for microbial biosignatures, where biosignature is anything that sort of is indicator of life. Now, one of the biggest challenges, though, is you can look at something. This is what's called a stromatolite right here. And they look like, you can see them in a place called Shark Bay in Australia. They form in the tidal zone where photosynthetic bacteria are basically sort of forming, they form these layers as the bacteria try to get up towards the sunlight to do their photosynthesis. And these structures have existed for 3.5 billion years on the Earth, and they leave a record. They leave evidence in the rock record. So that's a physical structure in the rock. But the other thing, and so if we see that on Mars, we get really excited. But the thing is that we really need additional information, like chemical information, for example, isotopes of particular elements like carbon or oxygen, or organic molecules, or even certain minerals that we know are formed by biology. And so that's one of the biggest questions, is how do we detect these ancient, possibly non-Earth-like life? So this mission has 4 ambitious goals. The first, of course, is the geology, because the geology provides the context for the environments that were there. The second is what's called astrobiology, which is essentially the search for life outside of the Earth. The third is to collect and cache samples for future return to the Earth, and I'll explain why that is later. And the fourth is there's another objective which relates to humans going to Mars, which is to pave the way, prepare the way for humans to go to the red planet. Here's our rover, and I'm going to go through these different instruments very briefly. I'm going to sort of more to highlight some of the recent results, but you can see here it's about the size of a small SUV. It's essentially the same construction as the Curiosity rover. It has a radiothermal isotopic generator, if I've got that right, RTG battery pack, basically, which powers it, so it doesn't rely on solar panels. It has a mast here, which stands just over 2 meters, almost 2.5 meters high, with a couple of cameras on it. There's a weather station here. There's a subsurface radar, an interesting experiment called MOXIE, and then out on this quite beefy arm is the what's called Sherlock, which is a spectrometer with a sidekick camera called Watson and Pixel. So I'll go through these. So starting with the mast, we have Mastcam Z, and this is a camera that can take stereo imagery with the ability to zoom tremendously. I don't have that information actually at my fingertips, but it can zoom. We already have images up to 2.5 kilometers away with remarkable resolution, as well as to do things looking at different parts of the spectrum, including into the infrared. The SuperCam is a laser, which is really, really cool. It can shoot up to 7 meters away, 2 to 7 meters away. The laser vaporizes the rock, and the light that comes from the plasma from the vaporization is interrogated essentially with a series of instruments, both infrared spectroscopy, Raman, and others, and there's even a microphone to hear the sound of the rock getting zapped to tell us what the rocks are made out of. So we can get the composition of the rocks and the mineralogy of the rocks from a distance. On the arm, we have Pixel, and this is it's an X-ray fluorescence instrument, so that allows us to measure the chemistry of the rock at sub-millimeter scales by basically putting an X-ray beam on and looking at the fluorescence that comes off. And then we have Sherlock, which is a ultraviolet, Raman, and fluorescence spectrometer that can, again, sub-millimeter, basically sub-tenth of a millimeter spot size, to look at mineralogy, and also it's able to detect organic compounds because of the part of the spectrum that it works in, this deep UV. And then the Watson is a high-resolution color camera for microscopic imaging that goes along with Sherlock, and these are meant to work together. So here's actual test data from stromatolites that are 2.7 billion years from Western Australia, and so here you can see essentially what it would look like with the Watson image. There's a part of a rock hammer for scale, these layers, and then here's a zoom in, and then to show some of these layers looked at with Sherlock along the top and Pixel along the bottom. So Sherlock will give a context image as well as signatures of particular minerals like chert, in this case chert, dolomite as 2 minerals, and then organic matter. And then Pixel gives the composition, so looking at where it's higher in iron or higher in other elements. RIMFAX is an experiment that uses ground-penetrating radar at these frequencies, and that gives us the vertical resolution between about 15 and 30 centimeters up to about 10 meters depth, depending on what we're actually roving over. And it measures every 10 centimeters along the track. It basically just operates whenever we're moving. And so this allows us to potentially, say if we're looking at layered rocks, to actually extend those into the subsurface and tell us something about the local geology beneath our feet. And then we have META, which is a series of environmental sensors that record things like dust properties and wind speed, pressure, relative humidity, etc. Then we have MOXIE, and so those, the ones I described up to now, are all parts of the rover for the exploration. This is the part of the fourth objective or goal for the mission, which is to demonstrate a technology that it will be important for human exploration. In particular, the generation of oxygen, an important thing for astronauts, future astronauts to breathe, as well as for propellant. Because if we can send something that will go to Mars, an instrument ahead of humans going, that can sit there and take in carbon dioxide and then electrochemically split it into oxygen and CO and capture that oxygen, then it can build up a source of oxygen that the astronauts can use once they get there. And we don't have to spend the money and fuel to bring all of that with us. And on April 20th, the first test was done. It produced oxygen at a rate of about 6 grams per hour. It produced just under 6 grams in this test, and that's enough to keep an astronaut healthy for about 10 minutes. So you'd have to scale this up significantly if you're going to do this, but it demonstrates that it could be done. And we also have delivered Ingenuity, a small helicopter, to the surface of Mars. It was literally strapped to the belly of the rover, as you can see here, with a cover on it, which we deposited elsewhere. Then we went over to this airfield, which has actually been called the Wright Brothers landing area or flight zone, because it is a pioneering type of technology demonstration. So this is not actually part of the overall mission. We were the aircraft carrier that delivered it to the surface and set it down. And it has performed spectacularly since, and I'll come back to that in a minute. But it is the first powered flight on another planet. It's actually done 5 of them now, as of today. And it's solar powered, as you can see here. And the key thing here is that you have these rotors that rotate in opposite directions, and they go almost 2,500 RPM, because the atmosphere of Mars is 1/100th the pressure of that of the Earth. So they have to go that much faster in order to get lift in the Martian atmosphere. It is good that you on the plus side, you have the lower gravity, 1/3 gravity, so that you don't actually have to lift as much because of the gravity relative to the Earth. But all of these things had to be kind of deduced and engineered for prior to landing on Mars. And as I mentioned, it's been highly successful so far. Okay, before I get into some of the recent results, let's talk about the fact that this thing has a lot of cameras. The ones that I mentioned, but also hazard cameras, which are stereoscopic cameras on the front and the back, full color cameras for navigation. And we're actually just gearing that up. We're actually gearing up to be able to enable the rover to drive an auto nav, basically automatically navigate. If we tell it to go 30 meters over there, it will actually navigate to that location while avoiding hazards along the way. But I want to talk about the entry, descent, and landing cameras and the whole process of landing this rover on the surface of Mars, because it was quite a spectacular event for those of you who may have followed it or maybe who missed it. So the timeline, to step back, of this rover was that the landing site, Jezero Crater, was selected in November 2018 in a workshop. I actually was able to attend that. The rover had been designed and was being built, and then it was launched July 30th of last year. And here's a great photo from a fellow named John Krause, who was in a Cessna 172 about 5,000 feet over Cocoa Beach during the time of the launch. It must have been spectacular to see. And then over the next 6 months and 19 days, it cruised to Mars and then successfully landed on Mars on February 18th of this year. It's a 471 million kilometer trip. It was launched at a time when Earth and Mars were quite close to each other, and then because of the orbits, it had to spend that time catching up to Mars, kind of coming up, essentially kind of come up from behind it from an orbital perspective. And then it had to go through the 7 minutes of terror. This is the cruise. This is the spacecraft here up in the upper left with the cruise stage, which is basically the part of the sort of ring that would enabled trajectory corrections along the way. It turned out it didn't need hardly nearly as many as were planned. It just was able to go right, basically thread the needle, and it was right on target. And then so that separated. And then atmospheric entry, and this is where this capsule, so the spacecraft is enclosed within the heat shield and the back shell, would hit the top of the Martian atmosphere, start to decelerate because of friction, and then when it got slow enough, supersonic parachute would deploy to slow it down further. Then the heat shield would separate, and then a very important technological advancement here. At this point, it would get radar lock on the surface to tell exactly its elevation, its altitude, I should say, and then what's called terrain relative navigation would kick in. So this is where maps of the landing site were already loaded on board the spacecraft, and it was looking down at the surface, and the computer on board was registering features of that surface against the maps that are in the onboard computer, and then finding a solution for that. And those maps on board had zones which are, please don't land here, these are okay to land. And so what it did was it then found that solution, the back shell would then separate, and then it would enter what's called power descent with this descent stage rocket kicking in, to slow it further, but also to move it laterally in order to avoid any dangerous areas. And then it did what's called the sky crane maneuver, which is when it got to a certain altitude, it would lower down on 3 tethers. It would lower the spacecraft down and set it down gently on the surface. The tethers would separate and it would fly away. Now, because we're on the surface of Mars successfully, all of this went well, but I want to give you a sense of just exactly, I'm going to show this video which shows you the different stages. But just to give you an idea of the accomplishment from a technological perspective, because the other thing to keep in mind here is that the time it took to, at this stage, to send a signal to Mars and back is 11 minutes. So there's no ground in the loop here. There's no way anybody on the surface of the Earth could control any of this process. It all had to be automatic. And so that's why they call it the 7 minutes of terror, because of course, as we're getting the signals back to mission control, it happened 11 minutes ago. So you don't know what's happened until you get the signal back. So the following video that I'm going to show, and I'll just double check to make sure, yep, share computer sound. And actually, I will also into the chat, I will put the link in case this doesn't work or in case it's choppy for you, but I will play this. So what we're gonna see is a series of videos from basically off the shelf, basically GoPro cameras that were mounted on different parts of the spacecraft, on the bottom of the spacecraft, on the top of the deck of the rover, on the bottom of the sky crane, we call it, or the descent stage that you see in the upper left there, on the top of the sky crane, looking in different directions, and they've been pieced together with what was happening in mission control as the signals were coming back from Mars. So I'm going to play this, and if someone could just flag me if you don't hear anything as I'm doing this, but I'll just play this, and I got to make sure I don't touch my computer because it'll mess it up. I'm not going to comment either.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Well, I can tell that was a really exciting moment to watch that, or to even just listen to that, and then to see that later. At the first, there were evening science team meetings the evening of, and then through the weekend after the landing, and we saw thumbnail videos of the videos that you saw there on the Saturday night, and people were just, I mean they were just little pixelated thumbnail videos, but it meant that they were like the preview for what was going to be downloaded from the spacecraft later, and it was just phenomenal that we could not only do this but actually document all that. And there's two things I really like about that. One is that you get to see, well, first that, you know, we landed this spacecraft on Mars in such an amazing way. But the second is, and I think maybe Simon can relate to this, it's like you're in a helicopter at the end. It's like you're actually setting down on the surface of Mars, and you can see, as you're coming in, you can actually see the context. And now that I know something, we start to explore the geology of the landing site, I can recognize certain features, and that's pretty close to true color, what you would see, because those are basically, you know, your kind of off-the-shelf GoPro video cameras. That's kind of what you would see. And so that's really quite amazing. Now, as soon as it landed, it had the command was to take a picture with the lens cap on through one of the hazard cameras, and that's what this is. So, but the lens cap is clear, and so that's why it has this black and white look to it, so you can actually see through. And this was to verify that indeed that it did successfully set down, and And so this was the first image that was released, and it was taken just 40 seconds after landing. And then this image was taken 10 to 20 seconds after that, and this actually catches the plume from the from the descent stage, basically the sky crane that flew off. It captured that, impacting the surface off in the distance, about 600 meters away. So really kind of cool. And then, of course, the first images, this is actually the first panorama from the Mastcam Z after the mast was stood up on the third day, and then did this is part of the panorama. You can actually see some of the blast areas where the dust has been cleared away by the thrusters. In fact, so there was probably some baking of the rocks going on here as well. And sand dunes, this one was partially obliterated by that. And then you can see off into the distance, this is Jezero crater. We're sitting inside Jezero crater, and we could instantaneously, we could already start to see some of the features. Now, why did we choose this particular location? Well, here's another version of what you saw earlier. So this is Isidis impact basin here, which is thought to have been formed about 3.9 billion years ago. And these are these Neely Fossae, these features that may be fractures related to the Isidis basin. This is Syrtis Major. These are a series of lavas that were formed around the 3.5 to 3.8 billion years. And then at the margin on the northwest part of Isidis is Jezero crater. And the intriguing thing about Jezero is that it like other craters, it had a valley. It has a valley here called the Vallis that carried water, carved this valley, and flowed into Jezero crater. The timing of that is thought to be about 3.5 billion years ago, maybe 4 billion years ago. And it formed what's called a delta. And it also had an outflow channel. But based on most estimates, it may have been filled at some point with between 100 and 200 meters depth of water. This is the landing site where we ended up. So just for context here, so this is the ellipse where we knew we could put the rover down with the terrain of relative navigation. The most likely spot was over here, just off of the delta, but we ended up over here. And it turned out this whole area here is a danger zone for the rover, for the lander system. And so we ended up diverting. You could actually see that in the video, ended up diverting away into this zone right here. And in fact, it ended up in a zone very narrow between two danger zones. That being said, it's okay for us to rove around in these areas, but in terms of landing, the landing site was subsequently named Octavia E. Butler after the science fiction author. Okay, Jezero crater. This is more so the geology now. This is the crater. This is our playground for the next several years, which is the delta. And this is a classic delta that basically indicates that there was water flowing in, carrying sediment from the valley and then into a standing body of water, and then that water slows down and the sediment gets dropped into the lake itself. We know that there's intriguing indicators of different types of minerals from orbit. There's what's called smectite, which is a type of clay. There's also carbonate, which is intriguing along the margin of the lake, the ancient lake. And then there's a signature of olivine down here in this area just west of where we landed. And all of this is sort of the context for our exploration, trying to understand what exactly types of rocks we're looking at. But the point is that we are in an environment that may have hosted life. Once we land, of course, let the speculation begin. This is from an early press release where we were just starting to look at the rocks, and all you really do is you describe them. So we can see dark rocks in the distance that are more sticky-uppy. We can see flat, light rocks. We can see other rocks, especially right by the wheel of the rover, that are holy rocks. They have holes in them. And at this point, and even now, we're not exactly sure the type of rock that we're looking at. It's most likely sedimentary or igneous, but we're not exactly sure which one. but anyway, so we could start to speculate, and of course start to understand. Now, a little bit about the successful helicopter mission. This is Ingenuity has a camera on the bottom. Ingenuity is the name of the helicopter. Has a camera on the bottom, black and white camera, to look down. It also has a side-looking camera angled about 45 degrees. It's a full color camera called a return to Earth camera. It's basically a cell phone camera. This was a low-cost kind of technology demonstration, and this is a beautiful image that it took on the third flight, I believe it was, because every subsequent flight, every flight was a little bit higher. The first flight was 3 meters up and then down. The second one was 5 meters up and then down. This 5 meters up, over, and then down, and sort of further up and further distance. And in this particular one, it went high enough to be able to see us off in the upper left there. So, in fact, the rover is here, and the landing site is over here. By this point, we'd gone off. We'd dropped what's called the belly pan to expose the Ingenuity. We'd driven back to the landing site area to drop the Ingenuity. And then we moved off at a distance. We're about 75 meters away from the helicopter at this point. And this just in, a press release earlier today is that on flight number 4, the microphone that is on Supercam, the laser gun basically, was able to capture the sound of the helicopter flying in the Martian atmosphere from about 75, 85 meters away. And they weren't sure that it could be done, but they listened and were able to do it on this flight. And you can see a video where they've synced it up and they've narrowed in on the frequency that you can hear this hum of a helicopter. It's really quite amazing, not only to see it actually lift off and fly, in that case, about 100, 110 meters and come back again, but also to hear it while it's flying. And where things are at now is flight number 5. I actually didn't check before this, but we were supposed to get the data down a few hours ago. For the first time, the helicopter is moving away from Wright Brothers Field, and it is moving further south, some 220 meters. It's going to go even higher. We'll have gone even higher, 10 meters high, and flown over 200 meters and set down in a new landing site. And this then starts a new phase of this. It's no longer a technology demonstration mission. It's going to have its own operations, not as frequent flights, but it's actually going to be exploring the helicopter as a means of supplementing or augmenting exploration missions. So it will now go off and do these reconnaissance sort of sorties, map the area. They'll stitch together, like they did for this one, they'll stitch together the images into a digital elevation model and then find a new landing site. And they'll do that basically as long as the helicopter will last, probably until about September. Okay, and then we have the imagery that's come down most recently. So this is now from a couple weeks ago. This is from the Van Zyl Overlook. So it's basically the location where the rover was just then. Van Zyl Overlook was where we parked while supporting the helicopter flying. And this is a panorama that shows what we're looking at. So we're seeing things like more flat-lying, light tone rocks, more dark rocks that are more rubbly. And then this continues over here. And then off in the distance, this set of cliffs here is the front of the delta. And over here in particular, this is a feature called Kodiak. And this is a cliff that we've imaged it in different times of day now to see different lighting on it. And it is absolutely spectacular. This is thought to be kind of a remnant of the delta. So it was once much more extensive and has been eroded back, and it's sort of a mesa left over. And what you can see in here, and geologists among you may be able to see that there are cross beds in here and other features that are strongly indicative of the delta environment that existed, and tell us something about the energy of the water that was coming in and depositing these sediments, and something of the history already, even before we start to get up close to these rocks. These are 2.5 kilometers away at this stage. Not only that, in the foreground, we have this area where we can see a lot more detail of the dark tone rocks and lighter tone rocks here. And because of the spectroscopic aspects of this mission, we are also getting more indications of the minerals that are present in these rocks, both in the far distance and in the foreground. So lots more exciting things to come. But all this to emphasize is that we are in a river delta. Here's an example, and this is a habitable environment. You can see the type of environment we're talking about, a river delta where the river flows in, brings in the sediment, and then deposits this delta feature. And so this is the artist's impression of what it may have looked like for 4 billion years ago, 3.5 billion years ago, when there was liquid water stable at the surface and flowing in and filling up this Jezero crater. And that's really what we're doing. We're exploring an area where we think that the environments were habitable. The rock record will tell us something about whether life was there. Now, one of the important things to know about this mission, and where I come in, is that in the core of the mission, the rover carries a sample caching system. And it is designed to allow us to collect and store Mars rock on the planet's surface for future return to Earth. And the business aspect is actually here on the arm. This big cylinder here, it's something like, I think it's 83 centimeters long. It's quite big. You can actually see it on the top of your screen here, this gray barrel that's embedded within the arm while it's folded up. It is meant to reach out to rocks, and it interfaces with the rover through this cylindrical thing here, which is called a bit turret. And what it does is that allows this arm to mate with the front of the rover. I'll go back here. It mates with the front of the rover here and takes a bit and a sleeve out of the rover belly. And so it's mounted in the coring device, and then it's a percussion coring type device. It will actually core a rock sample into a sleeve. The sleeve then goes into the belly of the rover underneath, where it gets imaged, and then it gets sealed up and kept on board. The samples look like this. This is 1 centimeter for scale. So depending on the size of your screen, it might be actually pretty close to actual size. And the idea is to collect 30 or so, hopefully at least 30 individual rock specimens, rock and regolith soil specimens, and sealed inside of these tubes. And the idea is we'll carry them along with us, and then we'll put them down into a depot or a cache at different points in the mission. And this is an early sort of concept for this, but let me just show you kind of some of the planning that was done. This is before we landed. We planned out, okay, if we land here, what types of rocks are we going to look at and what samples might we collect as we're heading out of Jezero crater. So here we would collect samples of the crater floor, what's called the fractured rough that we actually ended up landing on, and we would head up onto the delta. We would collect perhaps a sample of the delta itself. There's indications of carbonate and olivine minerals in some of these rocks. There's an interesting one of hydrated silica, so we might collect that sample. And then we go up here and collect another sample that might have carbonate in it. And then we would collect a sample of the crater rim, and then we would put a depot down of, in this case, in this planning anyway, 7 or 8 samples. And then we would head on outside of the crater. So that would be the first cache of samples. And the first cache would look something like this. And this would be where we would put down samples along the bottom here. But actually the planning is that we would take duplicates of almost all of the samples that we collect. And we would put half of those down, a representative set down in the first cache, and they would carry the duplicates of those with us in the rover belly as we head out of the crater. So by the end of year 3, so basically by 2024, we would put down a depot of at least 8, maybe 10 samples, and then we would carry the rest along with us outside of Jezero, and then we would continue our exploration. And this is just based on some planning. Again, this is sort of one scenario, but there's all kinds of other geology to explore outside of Jezero. And by the time of 2028, we would have a final depot that would be all of the duplicates from inside Jezero, plus all of these, whatever else that we are able to collect outside of Jezero to form a depot of actually more like 30 samples total. So this is really exciting, and it's especially exciting for someone like me. And the way I got on the mission was about time flies, 2.5 years ago now. I applied to NASA to become a member of the Mars 2020 mission as what's called a participating scientist. And so I was brought on, I competed, I was successful. I was brought on as one of 10 people from the NASA call. Of course, I can't get NASA money because I'm here in Canada, so the Canadian Space Agency essentially funds me for this. So I'm the only CSA funded participating scientist for return sample science. But then shortly after I was added, the PI of the mission, Ken Farley, called me up and said, would you be willing to serve as a member of the Project Science Group, which is essentially the leadership council that helps define and refine the science goals and strategies for the whole mission, which I said, yes, that would be fantastic, thank you. So my colleague Tanya Bosak from MIT and myself are the two representatives of return sample science for this Project Science Group for the entire mission. And we have something of 475 scientists on the whole mission, and there are 15 of us that are actually return sample scientists brought on to advise the mission on where and when to sample. I was really excited to get selected for this. My 13-year-old self would be super excited. This is me at that age. And it was around that age that I said, you know what would be fantastic is study the geology of another planet through the samples. And this was thanks in part to my parents. My mom, retired librarian from the Ottawa Public Library, children's librarian, who got me into reading, of course, early on, and science fiction. And my father, retired curator of the National Meteorite Collection. So I was exposed to rocks and books when I was a kid, and really took to geology and science fiction and put the two together in my 13-year-old brain to say, hey, I really want to be involved in this. And so here I am. So it's the first step basically in actually being able to work on samples that come back from Mars in the future. Now, in the interim, I did, and one of the reasons I ended up on this mission is because I worked on Martian meteorites. And just a brief thing about that is that we have about 160 rocks from Mars that have been found all over the surface of the Earth. They get delivered to Mars through an impact on the surface of Mars that accelerates rocks at the surface fast enough to leave Mars gravity, and then they come to the Earth as meteorites. None of them are sedimentary rocks with green slime on them, by the way. This artist's impression is meant to show something else, but they're igneous rocks. We don't know exactly where they came from, but they're all igneous rocks, and they're almost all much, much less than the rocks that we're exploring in Jezero crater, because there's actually a bias. There's a bias towards the strongest rocks, essentially, the ones that are going to more likely make the trip or survive this impact process blasting off the surface of Mars. So we have 160 rocks from Mars, and 82% of them are all less than 600 million years old, basically lava flows probably from some of those areas like Tharsis or Elysium. And so there's a bias in the sampling, and so instead of nature choosing the samples for us, we're sending a rover to actually go and choose the samples, and hopefully then find that evidence for ancient life. So we're not going to bring the samples back. An important note here is that this is the start of a massive international campaign to return samples from Mars. So we are here with sample collection with Perseverance. And our first sample, by the way, we'll probably collect in early July because we're still commissioning that part of the spacecraft. But we should be ready to go in early July. We will deliver those samples to the two caches by 2028. And at that point, the Fetch rover will gather up whatever cache is decided to be returned. We hope the one with more samples in it. It'll deliver the samples to the sample retrieval lander, which will then put them into a canister, blast them off the surface of Mars in a rocket, where the sample container will be released and captured by an orbiter, which will bring it back to the Earth. The timing of return to Earth would be 2031 at the earliest. And it's at that point when we will have all of the documentation when we collect these samples captured as part of the mission, and the justification for collecting those samples will come to bear on the analyses that we'll do on the samples when they come back. And that would promise to revolutionize our understanding of Mars's history, including the search for life. So that is it, and you can follow Perseverance as we explore. It's quite exciting. Of course, it's NASA. They've got lots of really great public outreach things to sink into, but hopefully that was a good overview of the mission and the excitement that it brings to me and hopefully to you.
Well, thank you very much, Chris. That was amazing. We do have some questions for you. So Andrew asks, I've seen the stromatolite analogy before, but without a moon driving a tidal wave on Mars. Is that a realistic structure life on Mars could have formed?
Can you say that again? Sorry. Okay,
I've seen the stromatolite analogy before, but without a moon driving a tidal cycle on Mars. Is that a realistic structure life on Mars could have formed?
Oh, I see. Yes. I see what the question is. Yes. Okay. That is a good point. You do actually need to have some kind of tides. Yeah, you're right. And so that's really interesting, right? Because tidal activity does need to be able to work so that the stromatolites form, because there's basically the microbes are essentially working their way up and making the layers. However, it's possible that if you have microbes, they will form these mats. And so in the absence of tidal activity, you could still have mats forming in shallow water that could still host microbial life. And then the question becomes, can you preserve that in the rock record? And if you do, how would you tell, right? And so that's the challenge that we have. We need to find the environment, and that might be, for example, in that case, that might be the margin of the ancient lake, those marginal carbonates that we talk about all the time, where there's a carbonate signature from orbit. Those would be a really good place to go and look if the rock structure is suitable, if it looks like it's the margin of an ancient lake, and then to hone in on the outcrops of rock that might host such evidence, and then to take the sample. And it's important to know that we will not really be able to tell for sure whether life was ever there until we have the samples back of the Earth. Really, we'll be able to say something about the environment and maybe detect organic matter if it's there, but we won't be able to tell for sure until we get the samples back and can throw everything that we have at the samples in labs on the Earth.
Okay, a couple of questions about the machine itself. What is the power source for the rover, and what is its expected lifetime? And all the equipment looks exposed. How is everything protected from dust and radiation?
Okay, so I'll answer the second one first. There is dust on the surface. It's going to accumulate dust. That's just a given. There are covers for the cameras. There's dust covers on almost everything. So it's protected that way. These are also meant to all of the equipment, the software, the hardware as well, is all radiation hardened, so that it's meant to have some redundancy in case there's cosmic radiation sort of damages it, that sort of thing. The power source for the rover is this RTG that I can't remember the exact meaning for it, but it's a radioactive source. So what it is it's plutonium, and it decays over time, and what it does is it heats it up, and then the heat provides charging to batteries. So we can essentially recharge the batteries for the rover through radioactive decay. And the lifetime is years. So the same power source is on Curiosity, and it's still going 10 years later.
Okay. Just a comment from Chuck. He said he loves the ASCII code on the parachute. And so related to that, is the lander sky crane now just scrap?
Yes, it is. It did its job. It sacrificed itself. It crashed, and it will no longer be functional.
Yeah, this is an interesting one. I said this question in the back of my mind too. How can we know that those rocks found on Earth actually come from Mars? What proof do we have?
It's the most common question I ever get. It's quite a remarkable story. So in 1976, there were the Viking landers, and they were able to analyze the Martian atmosphere. So to bring it in, put it through a mass spectrometer, and send the information back to tell us what the Martian atmosphere is made out of, how much carbon dioxide, different isotopes of different gaseous elements. And so we had that information. And then in the meantime, we had a series of meteorites that just didn't fit into any of the other meteorite categories. So they just looked different, and people had speculated that they were from some other parent body, asteroid or something like that. And but we didn't know exactly where they were from. And so it was a couple of really smart scientists at NASA Johnson Space Center who analyzed gas trapped inside of one of these meteorites. And they analyzed the gas and compared it to the composition of the Martian atmosphere and found that it matched. This was in the early 80s. And so because the Martian atmosphere is unique, there's no other atmosphere, we think, like it anywhere in the solar system. That's like a fingerprint. The other indicator, of course, I kind of alluded to it, is that they're igneous rocks, and a lot of them, actually most of them now, are quite young, and so they must have formed on a planet that had enough heat to continue to have erupt lava flows until, as young as 165 million years ago, which is the youngest of the meteorites.
Okay, thank you very much. That is the questions, and thank you very much for your presentation. That was amazing.
My pleasure.
Okay, we're going to move on to our observations here, and first up is Bob Olson.
NGC 2440 is a small planetary nebula and a challenge object from Oscar. It was first seen by William Herschel in 1790. It's about 4,000 light years away. I first thought, next slide. I first thought this red dot was a cosmic ray hit on my red images, but it shows up on each red image and none of the green or blue. It is really a red star. Rick Wagner identified it as a known carbon star. Next slide. If we zoom in, you can see that it's a very pretty nebula. Next slide. I think you missed one. Thank you. If we zoom in, you can see there's a very pretty planetary nebula. The white hot center of the nebula is the hottest white dwarf star yet discovered. Next slide. Polymer 5 is another challenge object. When I don't recognize an object, I do a bit of research, and in doing so, found this image. It looks very interesting, so I aimed my telescope at the area and took this picture. Next slide. It doesn't look anything like the image I found, but then I noticed that my view, next slide, was a much wider view than the actual object, and it really only showed the center. Okay, this is what my version looked like. Next slide. Okay, next slide. As you can see, I clearly need a bigger telescope. Next slide. The salt sprinkle in the middle of this image is UGC 6253, a dwarf spherical galaxy, which is another of Oscar's challenge objects. It is 780,000 light years from Earth, which is very close considering that Andromeda, the nearest galaxy to Earth, is 3 times further away. Next slide. M87 is the most massive of the Messier objects. It contains about 3 trillion stars, which is 15 times more than our own Milky Way. It also contains a massive black hole, which has a mass of approximately 6.5 billion suns. Next slide. Each arrow points at a galaxy. There are many more galaxies in this image. I just got tired of drawing arrows. Next slide. If we dim the brightness down a bit so the galaxy halo doesn't swamp the jet, we can see the jet coming from the black hole at the center of the galaxy. Next slide. Next slide. The cropped image shows the jet more clearly. Next. Okay, next slide. M5 is a pretty globular cluster high in the sky right now. Next slide. It's very easy to see why M64 is called the black-eyed galaxy. Next slide. This is M63, the sunflower galaxy. I kind of like this image. Next slide. I've always wanted to image Thor's helmet, but I should have actually imaged it back in February or March. I spent most of last month chasing it into the western horizon as it set. The bright lines of blue and red are caused by the interstellar gases being pushed around by a very active Wolf-Wyatt star, seen here in the hook of the upper blue loop. Okay, next star. M101, the Pinwheel Galaxy, a very pretty face-on spiral found just above the handle in the Big Dipper. Another pretty easy target in a visual telescope. Have a great day. Thank you very much.
Okay, thank you. And we're going to turn it over to Jim Sophia. Let me just spotlight you. There you go.
Okay, thank you. I noticed Simon's presentation on Mars slated for tonight, and I happened to come across an image I took of Mars in November of last year that I had not submitted. This was the month right after the planet reached opposition to the sun. I was using a Celestron 8-inch Smith Cassegrain with a Malincam DS10C Tech with a 2X power mate and a UV IR cut filter. The image was processed in Registax and wavelets. The scene was very good that night. Thank you.
Okay, thank you. I'm going to turn it over to Andrea.
Well, I have two galaxies, the Hockey Stick Galaxy, which is the upper one, and the Whale Galaxy. And the Whale Galaxy is the lower one, and it kind of looks like a sperm whale. And it's a very large galaxy that we are seeing edge on, and it's about the size of our own Milky Way, and it has its own little elliptical galaxy companion that you can see. The slides don't sort of do it justice. There's quite a lot of detail in that galaxy that it's fun to try to extract detail from that galaxy. The Hockey Stick, on the other hand, is a big distorted mess of a galaxy with little bits floating around. So it's a really tricky one, and it really, apparently the distortion is due to its gravitational interaction with the Whale Galaxy. Next slide. This was a wide angle shot that I've been trying out with a different telescope. I have a Red Cat 51, 250 millimeter focal length, and I have a new camera, the ZWO 2600, which is a much bigger sensor with a wider field of view. It's an APS-C sensor. And I targeted one of my favorite areas in Auriga. You have the Flaming Star Nebula on the right, looking at the Tadpole Nebula. There's the Fly and the Spider Nebula, and also M38, a star cluster up in the corner. Unlike the Flaming Star Nebula photo that I had last month, I used a hydrogen filter for this image. And so therefore you can't see the blue reflection nebula as well as you could last month, but it helps pick up all of the red in the sky. Next slide, please, Chris. And here again is another version of the Pinwheel Galaxy. I think it's probably my favorite galaxy so far this year in Ursa Major, a very popular visual target and also obviously very popular target to image as well. That's it, thank you.
Okay, thank you, Andrea. Taras.
We took this picture on March 15th from Fred Lossing Observatory, shortly after the sun set. The moon was quite low and behind the trees, brightly lit but by earth shine. And the evening was quiet and still, so it felt like you've just entered the scene where you will be the audience and participant of unfolding celestial events. And the moon was just there to welcome you. Its airshine showed up quite well in this picture, so I wanted to share it with you, hoping that it could reflect the mood. Let's go to the next slide. This picture was taken March 7th, shortly after Mars made its close approach to Pleiades, which was a day or two before that. It was a very nice view to behold. The planet was quite bright and yellowish, and the proximity to the asterism was a quite rare event to witness. This picture was taken with Canon EOS T3i camera, unmodified, with 135mm f2 telelens on Star Adventurer mount. Let's go to the next slide. This is essentially the same picture, but with more processing and cropped. The Pleiades is the nearest Messier object to Earth, and it's almost obvious to, it's quite obvious to the naked eye in the sky. Galileo was the first astronomer to view the Pleiades through the telescope. He thereby discovered that the cluster actually contains of many stars too dim to be seen with the naked eye. Pleiades have long been known to be physically related group of stars rather than a chance of alignment. John Mitchell calculated in 1767 that the probability of a chance alignment of so many bright stars was only 1 to 500,000. So surmised that the Pleiades and many other clusters of stars must be physically related. When studies were first made of the stars' proper motion, it was found that they all are moving in the same direction across the sky and at the same rate, further demonstrating that they were related. Let's go to the next slide. And this was this was taken also with a 135mm lens and also cropped. The Rosette Nebula is a hydrogen 2 region located near the end of a giant molecular cloud in Monoceros. In the middle of it, you can see an open cluster, NGC 2244, that is closely associated with the nebulosity. The stars of the cluster have been formed from nebulous matter. This nebula and its cluster is 5,000 light years from Earth, measures about 130 light years in diameter, and is seen from Earth as magnitude 9 object, which is quite dim. It took about 2 hours to image this image with the camera and the same telelens. Thank you.
Okay, thank you, Taras. We're going to go over to Richard Taylor.
Okay, this is my attempts at some of the galaxy clusters. I had a lovely night out at FLO at the beginning of April, and aimed it at a spot where I couldn't really see anything with my eyes, but I knew this was a good place for galaxies, and I was really, really happy when I processed the pictures afterwards to find that I'd captured Markarian's chain, which I think somebody showed last month as well. Next slide is the labeled version. Lots and lots of galaxies. So I forget if I counted how many there are here, but there's 3 different M objects and all these different NGC galaxies and a few ICs as well. Just an amazing number. This is almost a full frame in my Z73 telescope with an M100 mirrorless camera on it. Next one. And this is my version of the pinwheel. I showed one like this last month, but then I took another night of exposures, so I got a bit more detail and a little bit less grain. It's interesting for me because this is the first time I've actually combined photographs from 2 different nights to be able to build up a better image. So I'm still learning the processing steps. Next one, please. And here's a couple of the challenge objects. There is the M96 was the beginner challenge. That's down a little bit towards the left-hand side from the middle. And there's also NGC 3389, which is the tiniest of the three in a little triangle at the top left. Next picture shows the labels for these. So this is in Leo, just about halfway along the bottom of Leo between Regulus and Denebola. And we've got M96, M95, and M105, and then the two little NGC galaxies up there as well. Next slide. And nobody showed the lunar challenge yet this month, so here it is, crater Reinhold, which is just a little bit south from Copernicus. And on April 23rd, it was a lovely night for the gibbous, waxing gibbous moon. And it was a little bit past the best time for the shadow effects, but I was very happy to see that I captured the double rim on the crater Reinhold. So that showed up very nicely. And my last picture is the entire moon that night. This is actually a panorama of two shots, two different views combined with my very old 8-inch Schmidt-Cassegrain, a Bausch and Lomb. So that's all for me. Thank you.
Okay, thank you, Richard. I'm going to turn it over to Jim Thompson.
All right. So this is my one image for the month. It's a closer in shot of the crater Reinhold that we saw earlier in Richard's photo. Two different times of the lunar month. Image on the right has the sun setting on the crater, and the image on the right has the sun rising on the crater, with the left image being just from a couple months ago. It's an interesting part of the moon to observe because of so many intricate details associated with the impact crater Copernicus. You can see there's a lot of hummocky terrain around the perimeter of crater Reinhold. Presumably that's debris that was cast out from the Copernicus impact. It almost looks to me as well that some of that debris has landed on the floor of Reinhold crater. An otherwise fairly featureless crater floor has a few odd bumps in it. So quite interesting to see. The bumpiness of the terrain is really highlighted with the low sun angle that I had on the 22nd of March. It almost looks like they're giant boulders on the surface, but I'm sure they're actually not probably all that tall, probably only 100 meters or so in height. That's it for me. Thank you very much.
Okay, thank you, Jim. Okay, so we've got our observing challenges for last month, and we did get some of the folks to bring those forward. Thank you very much for that. So what are our observing challenges for this month? Our beginner challenge is Messier 85. It's a lenticular galaxy in Coma Berenice, 60 million light years away, 10th magnitude. Next one is the intermediate challenge, NGC 4565, known as the Needle Galaxy. It's an edge-on spiral galaxy in the same area. And our next one is our advanced challenge, Leo 1. It's a dwarf galaxy in Leo. And all of these will be in our Amazing Astro Notes, which I know Gordon's going to get out to us shortly. And I believe we have a crater, yes, crater Landsberg, impact crater and Mare in Solarium. And this is our lunar challenge for this month. And here's a summary of our observing challenges. So thank you to Oscar, who pulls these together every month for us. It's great to have something to look forward to. Next slide. Okay, the Fred Lawson Observatory, while we were still in lockdown in Ontario, the decision was made that we should really close the observatory. So it is closed right now. We ask that you stay away from there. And hopefully, as our numbers continue to go down, maybe in about a month or so, we'll be able to reopen things. Here are some of the folks that help keep our club running. So Rick Scholes is responsible for the FLO Observatory. The Stan Mott Book Library is encased within the Canadian Aviation and Space Museum, so we don't have access to that right now. And yeah, these are the folks that keep things running for us. So thank you. We had up to 124 people at any point in time. Thank you to all the organizers and speakers. Special thanks to Dr. Chris Hurd, our guest speaker from the University of Alberta here today. And thank you to the RASC National Office for the use of their Zoom account. Any comments or ideas for upcoming meetings, please send them to me, meetingschair@ottawa.rasc.ca. I'm still looking for speakers for July and August. I've got everything lined up for June and September and October, but right now, July and August are very quiet. So if you've got some things you'd like to share with us, I'd be happy to get your suggestions. Okay, for those who are not members, we encourage you to maybe seek out a membership with the RASC. A regular membership is $88. Family membership is $82.50 plus $15 an adult, $8.10 for youth. And a youth membership is $53 under 21 if you're under 21, or if you're under 25 if you're still a student. Well, so what you get for this membership? Next slide, please. You get locally, you get access to the Ted Bean Telescope Loan Library. Once the museum reopens, you'll have access to the Stan Mott Book Library. As soon as the COVID ban is lifted, you'll have access to the Fred Lawson Observatory out near Albion. And then nationally, you'll get the Sky News. This is the Canadian astronomy magazine, comes out every 2 months. And the Journal of the RASC also comes out every 2 months. Around December timeframe, you receive the Observer's Handbook for the current year. And monthly, Gordon Webster sends out Astronauts, which is our local publication. You get it in a PDF format. So thank you very much for everybody coming out tonight. And we're finishing right on time. I figured about 9:45, so that's super. And again, any observations and ideas, please send them to me. My name is Dave Chisholm. I'm the meeting chair. Our next meeting is Friday, June the 4th, 7:30 p.m. and it will be on Zoom again. Thanks for coming out. Have a good evening.